Greeting everyone. In previous class we have discussed about the resistance and the relation with temperature, and so far for like 2-3 classes we have been discussing on the same topic. So this class will give you the final installment on this topic, and here we'll see some graphs and little bit of few different things, and maybe one question today also will do. Otherwise I might give you that question as a homework. Let's see. See, in previous class we have discussed that change in resistance is directly proportional to the initial resistance. So thereafter we got this relation R0 times alpha delta T. Right? Similarly, you can get the another relation that change in resistivity is also directly proportional to R0 alpha delta T. Remember, when I am writing this equation again, what I am implying that your length and area is constant. Otherwise, if you change the length and area, you will have the different values, or you have to bring some constant or something. But otherwise, this equation will remain same, right? And you can see there is a relation of delta R with delta T. So why we are discussing? Because today we are going to discuss the nature of resistivity versus temperature. From the equation it seems that it is pretty clear that change in resistivity is directly proportional to change in temperature. That gives you an idea that as temperature increases, resistivity increases linearly, right? Means it gives you the idea or impression that there is a linear progression of change in resistivity as temperature increases, right? And that is what we have to discuss. Okay, how the resistivity versus temperature graph looks, that's what we are going to discuss. Then that is very important graph, you need to understand, right? So by that logic it seems if I draw resistivity versus temperature graph for conductor, it seems the graph should look like this. This is your temperature or resistivity, and the another one is this. It seems the graph should be like this. Right? Let's say the temperature is in, if you want to have like Celsius or Kelvin, whatever you want to write, let's say it is in Kelvin, and it is your resistivity. So it seems that when there is a 0 Kelvin, that means absolute 0, your resistivity should be 0. And mathematically it is not wrong, because this is what we had the equation, right? This is what we have the equation. But even though it seems the correct, or it seems correct expression and everything is correct, the graph we got from the equation is correct. If you put the equation in the graph, you will get the same graph. But the thing is, this is not the correct graph. What we found that yes, resistivity does linearly increase when temperature increases, but this is only valid when the change in temperature is very small. At very high temperature and at very low temperature, the resistance does not follow the ideal expression, it varies. Just like I told you, alpha we think it is constant, but it is not actually correct. Alpha is also function of temperature, and how it depends on temperature, how it depends on temperature, that is all, that you cannot also simply write it. I cannot simply say that alpha is directly proportional proportional to temperature, or it increases linearly, or decreases exponentially, whatever you want to say. It does not follow any particular law. Also, one more thing before I progress, if you have resistivity versus temperature graph, you should know this equation is just like what? This equation is just like what? Y equals to mx plus c, x being your delta t, rho naught and alpha should be constant, so that should give you slope, right? But this is not true. Even though rho naught is constant, but alpha is not going to be constant throughout the temperature. And what the graph will look like, I will show you. What we found experimentally is this. That when temperature becomes 0 or it is near to 0 Kelvin, the resistance is nearly constant. Resistivity is nearly constant, and then it increases linearly, then it increases exponentially. Again, when temperature is very small, you can see resistance is nearly constant, resistivity is nearly constant, then it increases linearly for some time, then it increases exponentially, right? For very small segment from this to this segment, you can see here the graph is somewhat linear. So here it behaves ohmic. And what we are talking about? We are simply talking about conductor. I am talking about conductor. In conductor also it follows, or the resistivity, the alpha is nearly constant for this particular section, and if you go a little bit higher or a little bit lower, the anomalies you can see. The resistivity is not following, the changing resistivity is not following the linear expression, it is somewhat deviated. And here you can see it is nearly what? Nearly what? Constant, and here it is increasing exponentially. This is your what? Graph of resistivity versus temperature. And here we have in Kelvin. Okay, I will draw one more graph. So with same color. And that's what you have to do, make okay. So again, this is your resistivity, this is your temperature, again it is in Kelvin. The graph is going to look like this. In starting constant, then it increases linearly. In starting constant, then it increases linearly, then exponentially. This is your graph. It is just we are talking about conductor. In conductor also, this expression does not hold for very high temperature or very low temperature. At very low temperature and here high temperature, you can see the anomalies, right? So what I expressed in previous classes, that alpha being constant is not going to be true always. It is always going to be a function of temperature, but for small change in temperature you can take it as constant. Okay, so this is your what? Resistivity versus temperature graph for conductor. You can take this screenshot. Then we are going to talk about semiconductor, then alloy. Okay. This is your conductor. Now we'll talk about semiconductor. Resistivity versus temperature graph. Now we are going for conductor. Now we are going to discuss about semiconductor. The expression is same, but remember, whatever this expression I am writing, it is true for small change in temperature. Now, if you remember, alpha was negative for semiconductor, means as temperature increases, resistivity should decrease, right? Because conductivity will increase. And if you see the graph, it will look like this. This is resistivity, this is temperature. Again, I am drawing for Kelvin, and it will look like this. This is your resistivity versus temperature graph for semiconductor. Again, it was negative. Again, you could have got this straight line, but you are not going to get straight line. Just like I told you, the relation, the expression that it should behave like straight line. It is only true for very small change in temperature. If the temperature is higher, it is always going to have a curved graph. Whether you talk about conductor or semiconductor, it is always going to have a curved graph. That is your semiconductor versus resistivity versus temperature graph of semiconductor. These graphs are very important for any aspects. You must remember the graphs and their character. Now lastly we will talk about alloy. If you remember, the idea behind alloy was what? That even on increasing temperature, your resistivity should nearly be constant, or resistance should be nearly constant. It is only true when alpha is very small and positive. It is positive. So here, ideally, what you should get, this is what you should get for alloy. But again, this is not you are going to get. Why? I will show you. Okay, so the graph will be like this, and you can see the graph is straight line. Again, if I go below this temperature, above from this temperature, again it will have curvy look, but in most books they draw it like this, so we are doing like this. So here you can see, even though there is a change, even though alpha should be very, very small, you can see it is still forming a little bit of angle from horizontal. Means even though the slope is very small, but it is not zero, just like I told you. So the resistivity versus temperature graph for alloy is like this. And why it has very small slope? Because alpha is very small. Again, if you go higher, it will again going to have a curve shape, and if you go lower, it will have the similar character. It will decrease, then it will become nearly constant. That is your alloy. Still, it will have very small slope. Okay. Again, I will tell you, if you increase temperature much higher, means if you go a little bit higher, it will have the curvy nature, and so is true for very low temperature. So this is the typical conductor, semiconductor, and alloy. Last category we will discuss on superconductor. What is our superconductor? See, okay. So superconductor has similar behavior as your conductor. The only thing is, for superconductor, they have something called critical temperature. They have something called critical temperature. At critical temperature, what happens? Their resistance becomes, at critical temperature, what happens? their resistance becomes zero. This is the definition of your what? Superconductor. These are some type of conductor for which at the critical angle, critical temperature, the resistance will become zero. And there are many types of critical temperature, but that is not in this figure, but mostly they are made up of ceramic, niobium, yttrium. These types of material we have to make. These are not elemental, these are also some sort of alloy. And why we use it? Mostly like it is used to have the idea of we study about this. Why we use superconductor? One reason is pretty obvious. At zero resistance, there will be no wastage of power in terms of heat, so this circuit can perform much efficiently. Secondly, to understand the magnetic behavior, sometimes you need superconductor. Once we will start magnetism in matter chapter and moving charge, there we will actually have the better analogy on the superconductor. Also, if you search on YouTube or something, you can search on superconductor. You will see they sometimes dip in liquid nitrogen, which has like minus 180 degrees Celsius temperature, and then it hovers on the magnet. Somewhat like that you can see on YouTube. And once we will reach to the magnetism chapter, we will discuss what is the actual usage of superconductor. But here you can have the rough idea that if you have superconductor, they can be much more efficient to our circuit. The only problem is to achieve that character, you have to achieve critical temperature, and for whatever superconductor we have found, the critical temperature is always minus 180, minus 150, somewhat like that. And our circuit works on much higher temperature than I just said. So even though we have something like superconductor, but it is not going to be work in every circuit. So people are working on the superconductor which can have much higher critical temperature. The graph will look similar to the conductor. Just little bit anonymity you will see. Just like this, but here what you will have at some particular temperature, your resistivity will become zero. This is your resistivity, this is your temperature. At particular temperature, the resistivity will become zero, and this temperature is known as critical temperature. For example, for yttrium types alloy, the critical temperature is around minus 181 degrees Celsius, somewhat like this. So you can see the temperature is much lower, and most of these electronics does not function at that low temperature. So we are working on something like to achieve some superconductor which can work on much higher temperature. Got it? So these are the graph which is very important for your understanding on temperature dependence of resistance or temperature dependence of resistivity. These are your graphs. Okay, so for superconductor you only need to remember what is the definition of superconductor. These are the conductor for which at critical temperature the resistance becomes zero, and the graphs you have to remember. Okay. Okay. So here we have something for you at the end of the class. This is the question you have to do. Okay. I will give you one hint. See here they have given you a nickel wire connected across battery. Temperature of wire increased by delta T1 they have given, and they have said if the wire is chopped in half length, how many degrees. You can get the idea of question. So this question you have as a homework. So in next class we will discuss this question and one more question. And in upcoming 2-3 class, we will be discussing questions from like SBT, Pathfinder or Olympiad type question. JEE means an advanced question we will also discuss, but fairly we will target books like what I have mentioned. Okay. So at the end of the chapter, what our idea will be, at least 50% of the question of Pathfinder and SBT types of books we have done, or I have given you the fair idea to how to solve this set of question. Okay.